especially in our country where most structures are built in reinforced concrete. So nowadays things are no longer done manually, unfortunately. Right? Should I say fortunately or unfortunately? It is fortunately, right? Things are no longer done manually, and we have to be able to adapt to the new way of doing things very, very easily. Things are done with the help of software in order to get results as fast as possible and remain productive. Today, ahead of us, we have just 30 minutes to do a clear demonstration, step by step, of how to design beams, and we'll be very, very practical about it. So, on your screen, what you should see there is the distribution plan. Should I say distribution plan? No, the formwork plan, all right, of a particular building, of a particular structure, which is to support a slab, all right. So this is just the modeling that we shall be using, and we will go from there to see how to design a beam. So in real life, you may have a structure that is more complex than this, because as you can see here, it's an ideal structure. All right, the spacing between the beams here are equal. Following the x-axis and equal following the y-axis. All right, this is really an ideal scenario. So for a structural lambda, there are cases where you can find this, but for a structural lambda, most of the time the distances will vary. All right, but with what we'll see today, I'm sure it will be easy for you to adapt and model that very easily. So we shall be using the BS 8110, and our focus will be to design uh, the most loaded beam. All right, and obviously the most loaded beams here will be the ones, first of all, that span the largest. All right, as you can see, 8.5 meters, 8.5 meters. And we also see the way the distance, the slabs are oriented, right? These are one-way spanning slabs. They are not two-way. So it means that their loads are given just in this direction. So these slabs here are supported by these beams and these beams. This other slab here is supported by these beams and these beams, and so on. All right. So those are the beams that will be loaded. Obviously, the most loaded beams will be the ones in the middle here. So we shall just use this beam here, 3AD, all right, and this will be our beam of reference for this particular session. So we shall use the characteristic strength of concrete to be 35 megapascal, the strength of steel, both for shear and longitudinal reinforcement, to be 500 megapascal. Sorry for the little p here. And then that of the concrete cover for all reinforcements, we shall take 30 millimeters. And this is the geometry of the beam, all right? This is the cross section of the beam. This is normally the tributary area of the beam that we are concerned with, the tree, all right? So it will take 750, half this way and half that way, right? Will give us this distance again. And the breadth of the beam, B, is 300, the down span is 400, and the thickness of the slab is 150. Okay, so the columns will be 400 by 400, and then we'll have the dead load taken in this manner. The weight of the slab, we'll calculate it. We have taken the unit weight of concrete to be 24 kilonewton per meters cube. So we'll multiply it by the depth of the slab to have it in kilonewton per meter squared, all right? Because as we shall see, we will model a cladding, all right, that enables us to model surfacic load, which will then automatically distribute these loads to the respective beams. And then the finishes will take 1.5 kilonewton per meter squared, giving us a total for the surfacic load of 1.1 kilonewton per meter squared. Now the down stand needs to be set aside, all right, because here, if this is the whole section of the beam, obviously, right? So the beam normally is 550 by 300, as you can see here, 550 by 300. But part of the beam is included in the slab. And if we have taken all of this to be the weight of the slab, we have to take just this part to be the weight of the beam that we are calling the down stand here, all right? So we shall apply it linearly on each beam and take it to be 2.88 kilonewton per meter. And the live load will take it to be 4 kilonewton per meter square. So that being said, I think we are ready to move. We are ready to move to robot structural analysis to go ahead and and start our modeling. All right. Okay, so here we have Robo opened, and obviously to model is a beam structure. It's a it's a building structure, right? So we'll select the building design module right here. Okay, so waiting for that to open. So we'll be fast about our modeling, all right? We'll go straight to the point and then do everything that we need to do as fast as possible. So hopefully we all have some background in reinforced concrete design, and there is not much that need to be explained. Many of the features, cannot be explained within 30 minutes. So at least the essentials will be touched, and you will be expected to somehow go ahead and continue discovering the features as you go. But most of the essentials, we'll touch most of the essentials in this particular session. All right. Still waiting. This computer has become extremely slow. Don't know what is happening. All right. So Yoruba may apply blue. Okay, I'm the one that have changed the theme. So the very first thing you want to do when you come to Robo, obviously, is to first of all set your tools, right? You want to set your environment. So we'll go to preferences, and we are using the British standard. All right. So I'll first of all go to the language and make sure that I'm in Great Britain for the regional settings for the codes, right? And yeah, English, we are in English. All right. So that's all I want to do here. And we want to go to job preferences and make sure that everything is all right. For the units, we want to use the metric system. All right, that's meters, kilonewton, etc. And for the materials, yes, obviously British. And the concrete here will have to take C35. Okay, so you remember that our FCU is 35 megapascal. So just to be sure, we can go ahead and do some modification here, come under concrete, and then choose C35 to make sure that the properties are compatible. Okay, something we want to change here is the specific weight. We want it to be 24 kilonewton per meters cube, not 24.5 whatsoever. All right. So we'll just go right there and say okay. And that's that for the material. So for the database now, let's expand that. We want to make sure that for reinforced bars, okay, we will use let me expand this, the 2000 version, okay, not the 2005. We'll use the 2000 version and of BS8666, and the design code right here, we want to make sure that we are in BS8110, and for load combinations, that's code combinations, we also want to take BS8110. So with all of that, I think our design is set, and we are good to go. All right, so just click on OK and we can start modeling. All right. So the very first thing we want to do is to first of all represent our axes. All right. So you have here axis 1, 2, 3, 4, 5, and A, B, C, D. These are not yet the beams, right? They are just the axes that will enable us to draw the beams very, very easily. And to do that, we'll come right here to structural axis, which is the first point here. And following X, these are axes here following X, okay? All of them are separated by 8.5 meters, all right? So what we'll do is we'll just add is number of repetitions there is 3, and the distance is 8.5, and we can add that, all right? Following Y, we have 1, 2, 3, 4, the same distance of 3.75, all right? So it will be 4 repetitions, and the distance will be 3.75, and we can add that. Okay, we'll take just one level, one story, so that should do that, and go ahead and apply that. So the building design module gives us two specific views. All right, we have the plan view where we can see X, Y axis. So the plan view here is ideally what we have this way. Okay, something we forgot is to put A, B, C, D right here on the other structural axis. So we'll just go right there, and on the X, yes, we'll just choose the numbering here to be A, B, C. Okay, so we'll apply that, and that should change. We have our A, B, C, D. All right, so we have the plan view and we have the 3D view right here. Okay, so The plan view here enables us to model our structure in 2D format, right? Following the different levels. You can be on the base, you can be at the level of the first slab, etc. Right? But for now, we are at the level of the first slab and we want to model our beams. So to model our beams, the very first thing we need to do is to make sure that the cross section of those beams exist. All right. So we'll come right here and define those bar sections. Okay. So they don't exist here. I'm not saying any 550 by, what's that? 550 by 300. All right. So what we'll do is that we'll create a new section. Create a new section. Make sure that it is RC beam. All right. And here the B is 300 and the height is 550. Okay. We can call that beams. Okay. Let's just call that beams. What is left here? The material here, we want C35, not C30. All right. So we'll just add that. We'll add that. And for the columns, we can choose here RC columns, and then we'll have C35 still for the material. And the cross section of the columns we said is 400 by 400. Okay, the label name, the label we'll give here is just columns. All right. Okay, so what have we done? We've simply created two cross sections. Okay, we've simply created the section for the beams and the section for the columns, so that when we are drawing our beams, we can give them these specific cross sections. Good. So we can close that and start drawing our beams. All right. So to draw our beams, this is what enables us to do that. I will click right there, and we'll first of all start by drawing these beams in this direction here. Okay, so let me just draw this one here. Okay, and I'll copy this and then so that it can repeat itself here. I don't want to have to draw each of the beams this way. So to do that, I'll select the beam in question and then come right here to edit, move and copy. Number of repetitions here is 1, 2, 3, 4. So I want to copy the beam 4 times, and I want to copy it from this distance to that distance, and that's that. All right. Good. So now the other beams, this, woo, okay, not the problem. Okay, it's good. We like the flexibility of robot. So you can see here our model UB is not supposed to be UB, right? It's supposed to be RC beams, but we will change that. Okay, that's not the problem. In fact, let's just go right ahead and do that. Okay, so I'll select all of the beams. It's good to make mistakes at times like that so that you can show some more things, some more flexibility. The structure, where is that? Excuse me. So we'll select all of the beams and assign them the material, or rather the material C35 here, and then the section we want them to be beams. Okay, that's what we want. So it's reinforced concrete beams. Okay, good. So we are done with that. The next thing is the other beams in the other direction, right? So we have a beam from, let's not make the same mistake again. We can come here to RC beam and then choose the correct section beams. All right, that's what we had to do first. And then draw the beam from here to here. Okay, close. We can select that beam now and then copy it, right? Go ahead, edit, move, right? And how many times? 1, 2, 3. We want to copy it 3 times, and the distance is from here right up to here. 1, 2, 3, right? So that's that. Okay, so we need to make sure that that's actually correct. Good. So the next thing we want to model now is our columns. All right, and according to the structure, we have columns on 5, we have columns on 3, and we have columns on 1. Okay, all true. 5, 3, and 1. So the odd axes, right? So we'll just come right here. This is where we draw the columns. Select the right columns, RC columns, and make sure that we have selected our columns section, right? And here, Yeah, you just go ahead. We just need to click on the points where the columns have to appear. All right. So we have a column here. That's that. A column here. A column here. A column here. Okay. Another one here. Right here. Right here. Right here. Right here. Whoa. Am I? No, not there. Not there. I'm pressing Control Z to cancel the two previous occurrences. Okay. There were no columns on this axis. So it's down this way. So I'll just click here to activate this. And then one here, one here, one here, and one here finally, right? So we'll close that. Now we can view our structure. So this is what our structure looks like, okay? And we can even see the cross section. This is what our structure. Okay, so now we'll need to place a cladding on top of this surface to represent the slab, the floor that the structure is carrying. Okay, so to do that, we'll come right here to cladding, geometry, and cladding. Okay, and for us to be fast, because in this case we have a rectangle. Okay, contour is many times when you don't have a specific shape like a rectangle. Okay, if you have an arc to cover or something, you can take contour and cover that very easily by several points. But here we have a rectangle. Okay, so we just select 3 points and then the fourth point will close automatically. So we want to do cladding from this point, and this point. Are you sure? Good. Perfect. But there is a problem here, right? I do not see the parameters of the cladding. So the cladding here is supposed to be a one-way cladding, sorry. Okay? Because that's what we have right here. Where is that? Right here. It's a one-way. It means it is these beams that support the slab. The slab gives its weight only in this direction, not in this other direction. All right. So let's correct that. We'll just press Ctrl Z. Okay, and then come back to geometry, cladding. All right, and rectangle, but this time we'll say one way Y, right? No, one way X. Okay, one way X. Let's go ahead. We'll have this and then that. Good. It's one way X, right? So one way X implies that it gives uh, it gives its load uh, perpendicular to the x-axis. All right, and so that's what we have. This here shows the direction of the load distribution from the slab. Okay, so the cladding there is not the floor in itself. It is just a surface that enables us to apply surfacing load on a particular region. Okay, so it is on this cladding that we'll be able to apply surfacing load from the floor, the kilonewton per meter square load. So we don't have to stress to do the distribution ourselves. Okay, so the next thing now will be to go ahead and actually define those loads. Right, a dead load. We have just two loads here, dead load and live load. Right, dead load added, and we'll add the live load too, and close there. And now we can start defining and applying our loads. All right, so under dead load, I need to make sure that here is dead load. Under dead load, we want to define specific loads. The first is the load, as we can see here, the load, dead load due to slab and finishes, which is 5.1 kilonewton per meter squared. So I'll just go ahead and choose the surface load, and this is the uniformly distributed surface load here, and we want the value to be negative 5.1. Okay, kilopascal here stands for kilonewton per meter squared, so that's exactly what we want. We will add that. Okay, all we need to do is to go ahead and apply it to that cladding, and we can see it applies everywhere. All right, and then still on dead load, however, we have an issue, right? So if I go ahead and deactivate, sorry, the cross section, you will notice something. You will notice that there is a sort of, let me activate the loading here. Okay, the loading. Let's activate the loading. You will notice that, okay, Come on. So let me deactivate the loading and then activate it back. Deactivate and activate. So you notice that when I activate, there is some form of green that surrounds all of those members. That green is to show that the self weight of all of the members have been taken into consideration. All right. Unfortunately, as I explained in the beginning, the weight of the slab here includes part of the beam. All right. So we need to make sure that we add the weight of the downstand of the beam, which is the part of the beam that's not included in the slab, linearly on top of every beam. All right. So for that, I will select all of the columns. Okay. We'll select all of the columns. Let me do that selection again. Let me remove the row. Okay. So we'll select all of these columns. All of the columns selected. This is their value right here. I would like to copy the list of columns. So let me do something technical here. I'll make as if I want to ascribe a particular bar section. And this is the list of all the columns I've selected. So I'll take them. All right. And let me close. So we'll go now to the load table. The load table shows us all of the loads that we've currently added to our structure. That's what the load table illustrates to us. And as we will see here, automatically when we define a dead load, the self weight of all the structure is added. But we don't want the self weight of all of the beams. We want the self weight of all of the columns, right? So here I'll just say part of the structure should be taken into consideration, and that part of the structure should be all the columns. So I'll paste all of the number of the columns right here. Okay, so that's what we want, and press enter. Good. So now if we go ahead and activate this again, you will see that only the columns are green, right? And the beams are not green. So now the weight of the beam, part of the weight of the beam, which is the 15 centimeters included in the slab, is already included in this uniformly distributed. What we need to do now, all right, let me put the cross section of those beams again. What we need to do now actually is select the beams, all right, is select all of the beams and then add its downstand weight. All right, so what we'll do, I'll right click there and select all of similar cross section. So those are all of the beams. All right, and what we'll do is that we'll define the load of the downstand on top of each of them linearly. So the value here, according to what we have, is 2.8, and this 2.8 is 24 times 0.3 times 400, which is the height of the down stand. All right. So 2.88 will have negative 2.88. All right. So let me add that, and these are all the elements selected here, and we can just apply, and that's the load. All right. So in this way, the weight of the beams have been fully taken into consideration accurately. All right. So the next thing we want to define is the live load. We'll just click on that and we come right here, surface and that. So for the live load, we have a value of 4 kilonewton per meter squared. We'll just add it there, 4 kilonewton per meter squared. All right. And we'll just click on our slab. And that's that. The live load is added everywhere. So the loads are taken into consideration. The last thing we would like to do before actually moving to analysis is to do automatic load combinations, right? Robot gives us that possibility not to stress, but to automatically generate loads, all right, according to code standards. So for that, we'll come to loads and go to load automatic combinations, all right, and we'll choose full automatic combinations right here and go to OK. All right, so something should come up, something should come up. Are you sure I clicked on that? Automatic load combination, full automatic load combination. Okay, what happened? Load combination, automatic load combination, full automatic load combination. Something is wrong somewhere. All right, so I think I will quickly need to do something, okay? Because what's happening here is not normal. It's supposed to take me to the next step where I'm supposed to choose whether I want ultimate limit state, serviceability limit state, accidental load, etc. But it's just shutting down. I don't know what's happening. Okay, so let me try to just restart this file. Okay, so I'll save this. I'll save this. Let's save this as beam design. Okay, or let's say RC beam design. Okay, let's go. Let's go. Let's go. Let's go. Let's go. All right. So I'll just try to open a different project and then come back to this. All right. Let me open this 2D frame, for example, and then come back to this and let's see whether it behaves otherwise. Because what it's doing right now is not very normal. You know, softwares at times go crazy. At times, it just misbehaves in front of you. You don't know what's happening. So at times you need to do things a little bit differently. It's crazy how time can fly when I'm doing these things. For my time frame here, I feel like I've done only 5 minutes, but in real life, am I that talkative? All right, so we are back. So let me see what's happening. I want to go to load combination, automatic load combination, full auto. Wow. Wow. Okay, let's just launch the analysis and see whether it has actually generated the full load combinations. So to launch the analysis, we'll just click right here. Bar without properties. Errors have been found. Bar without properties. Do you want to continue? Yes. But which bar is that without properties? Number of element 22. All right. Section is not defined for the bar number 18. All right, let's see which bar that is. It's crazy. Maybe that's the bar that has been causing the error. So let's identify the bar 18. Which bar is that? So this is the bar 18. And I don't know how it succeeded in landing here without a section, but from all indices, it is there without a section. Actually, it's a bar that's not supposed to be there, right? It's not even supposed to be there. Wow. This is not something supposed to be there. How did it land there? All right, so let's just delete that. I hope it's leaving no node on the floor here, isolated node. Let's just delete that too. Okay, so let's go again and do the load combination and see whether that was what was causing the problem. Yeah, nothing has changed at that level, right? So we'll click on load combination. Okay, no errors, nothing. And for the loads, oh, it has generated the loads automatically. Fine, good, no problem. So long as the loads appear, right? So you see that it has generated ultimate limit state, everything according to the BS standards of 8110. All right. Good. So that having been done, normally if you try it in your own robot, right, it will show you the next step for automatic load combination. So certainly my own robot has gone crazy somehow in this project. I will solve that at a later time. Yes. So you can actually see the distribution of loads, okay, from this cladding. Okay, so for that, we'll come right here to display and go to loads, all right, and click here on load distribution region and click on OK. So this will show you how the loads have been distributed on each beam, all right? So you can see that this beam here takes half of the load that this beam is taking. It takes half of the load of slab here and half this way. Half this way for this beam and half this way. Half this way for this beam and half this way. Half this way for this beam, all right? So it clearly shows us that the loads were accurately distributed without us having to calculate the tributary area of each beam and all the like. Robot did that automatically for us, okay? So the next thing you want to do here is actually to be able to analyze any beam. So let's say the beam that we want, okay? What I will do here now, I will actually remove the cladding so that I can choose my beams very easily, Okay, so for that I'll come to display here and remove the cladding. Okay, so I can choose select my beam here very easily. Oh, why is this beam misbehaving? All right, let's go to the plan view, and the beam history is this one. All right, and come back to view. It should be selected now. Good, that's it selected. And what we want to do is to analyze the of bending moments, the envelope of shear, and the envelopes of axial load, for example, for that particular beam. So what you will do is you select the beam and you come here to results and go to detailed analysis. Detailed analysis will isolate that specific beam, all right, so that you can see what you need to see about the beam. All right. If I want to see the bending moment diagram of that beam, I will just select MY and apply, and that's that. Okay, but this case is just for the dead load. If I want to see it for all of the loads ultimate limit state, I will come and click right here. Okay, and as you can see, this is the value of the load for ultimate limit state. So normally this is symmetrical. It means the value here should be the same value that is here. The value here should be the same value that is right here. If I need to see it for serviceability limit state, I will have it there. All right. If I need to see the shear force, this is the shear force right here. I can just remove the moment, or I can see both. Why not? And apply. Okay, so you should draw the diagrams the way you just see. So when we say envelope, it means that it has taken all of the cases, all of the isolated cases and all of the combinations put together. Okay, as you see all of these lines like that, they are the moments for different cases. Okay, and it is showing you the maximum value for serviceability limit states all together in this case. And if you want for ultimate limit states, this is it right here all together. Okay, so it means that if I'm to design for the span, I want to get just one maximum moment for the whole of the span, I'll use 231.86, for example. All right, so that's that. So now let's focus on the reinforced concrete design of the said beam. All right, so let me remove all of that and close, and we can exit here. So now to design a beam, all right, uh, this beam in particular that we are interested in, you select the beam. Make sure that you select the beam, and all you need to do is come and click on this icon right down here. Provide reinforcement of RC beam. All right, so you click there, and life is good, right? You just set some parameters to make sure that everything is okay, and as usual, robot does the job for you, which you can collect in the background. All right, so I'm sure that when I plan 30 minutes for this thing, I did not take into consideration all this waste of time that the software is taking to load. Wow. All right, so we are there. So what we'll do is just to click right here on OK. Okay, so we're taking the simple cases and we'll just click on OK, because automatically, again, in this case, robot will do all of the load combinations according to the BS8110 standard that you chose. All right, so if you want to design for other standards, robot has a lot of them. The IS standard is supported, Indian standard supported, uh, ACI American standard is supported, Euro code supported for France, Germany. In fact, they have so many codes. All right, so if I reduce this, if I reduce and move this, we'll see the cross section of the beam right here. All right, so to remove all these long things, once you have zoomed, you just need to click on it. All right, and they will come to shape. So you can see these are beams 300 by 550. Okay, and these are the columns 400 by 400. V1, V2, our spans are called P1, P2, and P3. So to design that, you need to make sure, first of all, that your parameters are set right. And here are the parameters. We'll start with this one here because of time. Okay, we'll touch just the essential parameters. So in this case here, look at this. We have spans that go up to 8.10 meters. 8.10 meters, that's huge. All right, even for a beam of 300 by 550. Okay, so for sure, uh, I won't stress here. We said the concrete cover, this is the cover to in millimeters. We want to measure it from the transversal reinforcement because it's the concrete cover to all reinforcement. We need to make sure that it is fixed here so that it doesn't change during the calculation. Okay, we want it to be 30 millimeters as indicated right here. Okay, so if it was 25, you just put those values there to 25 and continue. All right, the concrete itself, these are the characteristics. C35 perfect. Longitudinal reinforcement. So you see that robot will do calculations automatically according to what you give it, all right? But it has a tendency of choosing a minimum reinforcement. So what I want to do here is good for you at times to choose the diameter of the bar that you would like to use so that robot dimensions according to that particular diameter. So I will choose 25 millimeters here, and this is because of the span of the beam and the corresponding depth, which is actually too large. Okay, the ratio is small somehow, so I will take large bars of 25 millimeters, and then transversal reinforcements we'll just take by 8 for that, and additional reinforcements I'll use by, should I say, by 12. All right, let me just use by 12 for additional reinforcement. Oh no, let me use by 4, by 12, by 14, and if you like by 20, 25, be free. All right, so we'll do that. And the next thing we want to touch is actually right here, reinforcement patterns, right? And the little things we like to do here is for the main reinforcement, we want a minimum diameter of 25, all right? To make sure that they choose that 25 as priority. Bottom reinforcement, allow them to choose the number of beds here automatically, okay? Yeah, maximum number of beds can be 2. That's okay. And for the top reinforcement, they should follow the same standard as the bottom reinforcement. Transversal reinforcement, I don't want these middle links, okay? I just want them to be like this or like that. All right. So what I'll do is that I will deactivate this. Okay, that was deactivated, and just leave those two. All right. Um is there anything I'm forgetting? I don't think so. So these parameters you're setting here, you can actually save them, all right? You can save them and store them in your own robot so that you don't have to repeat it each time you want to design for a particular project. So we'll just click on OK. And that's that, guys. It's as simple as that, all right? What you want to do now, so obviously there are more parameters here. You can go through those parameters yourself, okay? There's more to explore, but this was just to give you an idea of how to go about it. So what you want to do after you have done that is just come and click on this Start Calculations. You can click there and go to Calculate, and that should do the calculations automatically for you. If you want to see your reinforcement, you come right here to beam reinforcement, okay? You always have this window that appears here. I don't know how to set it off, but it is really annoying to have to displace this all the time, and each time you want to design a new beam. Anyway, that's out of the point. So that's the reinforcement done right here automatically by robot. All right, so that's cool. That's cool. So you can actually, this is the detail of the reinforcement. Okay, if you want to see this main bar, when you select it, they show you these are the bars here, these other ones here. So this is 25, this is 6 bars of 25 up here. Anyway, don't worry, we'll see the way they are being displayed down there. And right here you have 6 bars of 25 too, right here, and here the same thing. So the better way for you to see it, if you cannot really see it in this 3D, but you can actually obviously see it in the 3D if you zoom enough, right? If you zoom enough, we can actually see it clearly. But I prefer to see it with the drawing right here, okay? The detailing that will show us span by span what has happened, all right? And as a structural engineer, you must not cram what robot gives you. I should say that in passing. You should not just cram it as gospel. You should be able to analyze and see that it makes sense, all right? So at this level, they have used this AA, so it means when we cut here, all right? It is 3 bars down and 2 bars up, and those bars, the bars down is 3 bars of 25, as we can see here. 3 bars of 25, and up here we have 3 bars of 25. So it is certainly those two that they call, no, not the two. If I cut here, there should be 2 beds, I'm sure. All right, so one, we have 3 bars of 25, and then 5 here we have 3 bars of 25 down this way, and then we have our share links this way. All right, we have our share links this way, 4 of them spaced at 180, uh, and it goes on and on. So you'll notice that the spacing between the share towards the support is small, right? And as you go, it increases. As you go, it increases because the share diagram is maximum towards the support and then reduces in the middle and then maximum again towards the support. All right. So you need a smaller spacing to be able to support that. So that makes sense, and something like that. So this drawing, you have two possibilities. Okay, you can actually print the drawing and have it in the PDF format. All right, so let me choose here Foxit Reader and print all the pages and go to OK. All right, so it will print the drawings and then give it to you in PDF, or let me choose where to save that, in document, Autodesk Robot. No, let me say RC beam design here so that we can open it and visualize. Or as many times it is the case, you may want to have this drawing in a setting where you can actually edit the drawing, all right, to be able to suit what you have in the field. But what you have here is already a good working vantage point, right? Now you can elongate some bars and all the like to make it more feasible and more realizable in the field. But make sure that you never reduce the amount of steel area in a particular cross section. You may rather want to increase, but maybe not reduce, and not increase to the point that the beam is over reinforced. All right. So there is more we could do, and that we'll see maybe in upcoming training sessions, like being able to manually modify the reinforcement of the beam and then checking if your new modification can actually work. All right, that's also another possibility you can have in Robot. So if I have to save this as a drawing, I just need to come here and then you save in a different drawing format. All right. So if